First of all, I have to take you with me in the colorful world of hydrogen. Yeah? So, even though you know hydrogen has no color, it cannot be smelled, nevertheless, there is used something like a color code for different kinds of hydrogen. Yeah? So, what we are all aiming for in this process is here, the green hydrogen, yeah? Made from renewable energies and electrolysis. What we have today mainly is the gray, this one, the gray hydrogen, yeah, which is directly extracted from natural gas or maybe even oil. And then there are different ways. Yeah? So power mix, yellow hydrogen, red hydrogen from nuclear power plants, blue hydrogen. This is what the Australian would like to sell first of all. This means natural gas or also power generation from maybe coal and then doing carbon capture and storage, CCS. So taking out most of the carbon dioxide from the exhaust air and bringing it under the earth. We also can result in hard carbon here. This is a turquoise hydrogen, orange from biogas, and some more here. These colors are not not commonly used always in the same way. So take this as one of the definitions. But what is important about this is if people talk about the future hydrogen economy, most of the people are quite clear that for sure in the medium term, long term, the hydrogen should come from renewables and therefore there should be green hydrogen. But one of the big questions is if for the intermediate, especially for the market introduction, things like blue hydrogen, for example, are acceptable. So using fossil fuels to produce a hydrogen combined maybe with carbon capture and storage. And to be very clear, I'm absolutely convinced that we will need this. Yeah? Because if we want to convert, for example, steel industry, or I just mentioned there is a development of gas turbines, and just the testing of the gas turbines requires huge capacity, huge amounts of hydrogen, and we won't be able to deliver them now at the beginning from renewables, so we have to take them also from conventional sources, and when we can combine it with carbon capture and storage, then it is also from a climatic point of view acceptable. Yeah? There shouldn't be the pathway for the long-term future, but in between this is surely necessary. So synthetic fuels are also called eFuels. Yeah? So I use both terms. Could be methane, as discussed all the time already, CH4, or hexane, but also other light crude oil equivalents could be produced. What is more difficult is to produce something like bitumen as it's used for the building streets, for example. This is not what comes out of the normal Fischer-Tropsch procedures. So when we now look into the production of these methane or the e-fuels, so let me call the e-fuels are the liquids one, and this is a gas. Then it all starts with hydrogen and carbon dioxide as a carbon carrier. And we have different things here to look at. Sabatier reaction, Fischer-Tropsch synthesis, and maybe water-gas shift reaction. And I would like to go through these different process steps one by one. So the first is that we need a hydrogen. Now, the hydrogen has to come from, and we have different electrolyzer technologies available. I don't want to go too much into detail. This could be lectures on their own. There are the so-called alkaline electrolyzers. So this is the most sold commercial product in the world, traditionally producing hydrogen from electricity. This is relatively inexpensive, but has low current density, is a low pressure process, and is relatively slow. Yeah? So slow in ramping up and down power ratings. Therefore, it cannot be controlled so easily. But for example, one of the largest of these electrolyzers is installed at the Aswan Dam on the Nile in Egypt. Yeah, so the dam produces electricity, And the electrolyzers there are exactly used to produce fertilizers. Because the electricity produces hydrogen, then ammonia is produced, and from the ammonia we can produce fertilizers. The much more flexible technology are the polymer electrolyte membrane electrolyzers. Unfortunately, they use some very noble metals like platinum as catalysts, but they are extremely fast in ramping up and down, have a relatively high current density, so you can build them very compact. So this is a top technology of choice for if you need high dynamics. So at least part of the capacity would be good to have in the PM electrolyzer, simply because then we can follow the load curves very precisely. A more efficient technology are so-called high temperature electrolyzers. Generally, you could also split water into hydrogen and oxygen if you have very high temperatures, and the high temperature electrolysis is something like a compromise. So if you go to 700 to 100 degrees C and you add electricity, then you can produce hydrogen at a higher efficiency. But this is for sure, the one question is, where is the heat coming from? So if we have to take electricity to heat the thing up, then it is not efficient anymore. The other thing is that for sure always such high temperature systems are very slow in variations, because they have a large heat capacity, and you should also not let them cool down too often, because this typically also makes thermomechanical stress. Nevertheless, there are different high electrolyzer technologies. Unfortunately, the worldwide research in electrolyzers for a long while in the 2000 years was relatively low. All emphasis was put on fuel cells. Unfortunately, somehow, especially in Germany and Europe, the research on fuel cells, on electrolyzers, was not really supported a lot. I never really understood why, because if somebody develops fuel cell, he or she should also have an idea where the hydrogen comes from for the fuel cells. But this needs to be recovered now first quite significantly. However, technologies are available, but in a small scale, and this is what I would like to show you here with data from the International Energy Agency. The data are available here until 2020, and this is the global installed electrolyzer capacity. So the scale here is megawatts, and you can see Europe, China, Canada, rest of Asia, rest of world having a certain capacity, but in total something like a maximum of 300 megawatts of electrolyzer capacity in 2020. Electrolyzer capacity purely for the hydrogen production, which is not very much. And if we look to the technologies, we can see it is here the alkaline, which makes the largest share, the polymer electrolyte membranes, and then we have here high temperature processes. And the largest plant in 2020 was 20 megawatts. This all is not very large, and it becomes obvious that there is a long way to go for the worldwide hydrogen economy, because these are now projections of the demand in hydrogen according to different scenarios published by the International Energy Agency. So it's not my data, this International Energy Agency data, and they looked to the today's use of hydrogen. This is not small. As you can see here, this is something like 85 million tons of hydrogen are used today. So hydrogen is really a very important product, no question, but it is not traded internationally. And now, when going into the energy conversion scenarios, and this is just a prediction to 2025 and 2030, they predict that there is a significant additional demand in electrolyzer capacity, or first of all, in additional hydrogen demand. And if we just look at the numbers they attribute here to the electrolyzers, as you can see, they attribute also quite a bit of additional hydrogen production from fossils with carbon capture and storage or carbon capture and reuse here. But if I just look to the additional amounts predicted here for the electrolysis, yeah, so then we can see, or we can calculate what this means. Yeah, so for these additional 23.9 megatons of hydrogen, we need something like 1.1 terawatt hours of electricity. This is roughly 2 times electricity Germany is using per year. Would require 215 gigawatt of electrolyzers, if I assume 5,000 full load hours. And this would require something like 360 gigawatt in wind and PV, taking into account a certain full load operation. And if we go to 2030, then it is more like 3.6 terawatt hours, and the sizing is accordingly. So just to keep in mind, the 215 gigawatt of electrolyzers which would be necessary in 2025. And remember that I showed you that the existing electrolyzers in 2020 were 300 megawatt. Yeah, so this is a factor of 700 or something like this, yeah? Close to 1,000 at least. Yeah? So an enormous ramp up. Yeah? So orders of magnitude faster than we see it for the batteries. So at least technology is available, but not on this large scale as it would be necessary. Then CO2, we need the CO2, as we discussed already, we can get it from removal from the air, direct air capture. The concentration is low if we take it directly from air. If we take it out of some power plant processes, then we have a higher CO2 concentration. But we also, for example, need for the direct air capture today something like 1.2 megawatt hours per ton of CO2. Yeah? So this is surely an important parameter which determines also the cost, not only for the CO2, but for the negative emissions we have discussed beforehand. The CO2 capture is a process which generally is understood, but the sites which have been made up for demonstration are very small. Yeah, so you cool down the processed gases and then you can absorb them in some materials. You can extract it, and then you have to recover the materials for continuous operational cycle. So this is generally possible and gives you a good yield of the CO2. So then we would like to make methane from this. Yeah, so this is a so-called Sabatier reaction. This is an exothermic reaction. So you bring CO2 and hydrogen into a reaction, and this forms at the end CH4. So the methane molecule plus, in addition, water and lots of heat. This requires catalysts. Nickel is quite well suited here. This is at least a cheap catalyst. Pressures, yeah, maybe 10 to 100 bars, and an efficiency in the range of 80%. Some of the energy gets lost. For example, the water here still contains some of the energy. This can't be avoided. But once we have the methane, we then can go into the existing infrastructure, because then we have something which is really chemically equivalent, completely equivalent to natural gas, and all the existing infrastructures in industry and shipping and standards can be applied, and this is for sure helpful. Nevertheless, it costs energy. So we want to go towards the e-fuels, and typically, first of all, the synthesis gases are produced. This means we may produce CO2 plus hydrogen here as a synthesis gas reaction. This is not really the one where we would follow up in the pathway I just have shown, but this is a process which was discovered already 200 years, or at 1780, so a long time ago. So all these processes are relatively well known, but this also means they are limited by their chemical reactions, and we cannot improve them too much. Nevertheless, once we have the synthesis gas, we can go for the Fischer-Tropsch synthesis patent from 1925, so almost also 100 years we need for this Fischer-Tropsch synthesis. We need the carbon monoxide together with hydrogen. We then can form different chains of carbon hydrocarbons, and in addition we get water. This process takes place at different temperatures, around 150 to 300 degrees C, and different pressures. And depending on temperature and pressure, you get a different mixture in chains. Yeah? So you get different hydrocarbons, and this is what we have today from oil as well. Yeah? We have gasoline, we have diesel. These are simply different chains with different lengths of hydrocarbons, and they can be produced here in this process as well. But, and this is also important, you cannot say, I would like to have from this process, for example, pure diesel, or pure jet fuel, or pure gasoline. Yeah? You always get mixtures. Yeah? So, and this is the same if you process oil. Yeah? You cannot convert oil 100% to diesel, or 100% to gasoline. Yeah? This is why gasoline and diesel always shipped also around the world. Yeah? So Europe, for example, has a higher demand on diesel because many cars driving diesel. So we buy diesel from United States, and therefore in exchange they get gasoline. Yeah? So because we produce more gasoline than we need, and the United States produce more diesel than they need. However, also this, even though these processes are well known, the demonstration sites for this are still quite small. Yeah? So this is one pilot plant, and you can see pictures with ministers and so on. This is the future of our energy system and so on. Quite nice, but this system, this demonstration system, produces 500 liters of synthetic fuels, 500,000 liters of synthetic fuels a year. And just to give you a relation, because this should become fuel for airplanes, this is sufficient to refill an Airbus A380 1.6 times roughly, yeah, in a year. Yeah? One airplane 1.6 times. So this is not really a lot. Yeah? Nevertheless, there are targets to produce maybe 300 million liters of jet fuels in 2030, and the share of 5.7% of the jet fuel should become synthetic fuels in 2030. This is, by the way, politically speaking, or this is a target which is purely defined by politics. From a climatic point of view, this makes no sense. Because as I said, we can switch over to syn fuels or to synthetic fuels at any point of time for the airplanes. So there's no need to begin now. And at this point in time, we would have other opportunities to save much more CO2 emissions when we use the energy instead of putting it into these jet fuels. This is the least efficient way to bring energy we have into CO2 savings. And therefore, from a scientific point of view, we clearly say these type of targets given by politicians make no sense. Nevertheless, if you look to this from a from politics point of view, then things might look different. Because it is very difficult for politics to decide this industry or this sector have to do savings or changes, and the other can wait for another 10, 15, 20 years. For them, it's much easier to say everybody has to do savings. From a political point of view, I can understand this. From a climate protection point of view, these targets here make no real sense. Another site which was, or another production site which is often cited when it comes to the question of synthetic fuels is the one in Chile, built by Porsche. Porsche, I don't know if you know, Porsche builds relatively sportive, fast cars. And even though their best-sold car is an electric vehicle, they often claim that they need also combustion engines in the future, and they set up this demonstration site This is producing 130,000 liters of synthetic fuels per year. This, by the way, is sufficient for 138 cars to fuel them. They targeted in maybe to expand this by 55 million liters by the mid of the decade, and somewhat later already increasing it by another a factor of 10. But I think most probably Porsche, meanwhile, also got to the conclusion that this is not the future of their cars. For example, they have skipped the plans for building the huge wind parks which are necessary to produce electricity for this target here. As far as we know, they have not followed up on these plans. So even Porsche, meanwhile, is more or less purely on the electric trip. And this is another one, another system which produces synthetic fuels, 4.6 million liters for the chemical industry, mainly here close to Frankfurt. So with this, I would like to have a short look in demands in different fields. And I would like to start with the organic chemical industry. And I have mentioned this already this morning several times. And I just want to make a short calculation here with you to show what the challenges really are. Yeah. The German chemical industry has used, maybe 2 years ago, doesn't matter, around 18 million tons of crude oil and gas, not for energy purposes, but as a raw material. Yeah? About 18 million tons. Now the question is, if I want to produce this from hydrogen, I can calculate what this means in amount of hydrogen and energy. Yeah? So I can make an assumption that this is cyclohexane, which is used here. We know the weight of carbon and hydrogen, and so we can calculate some shares. We take into account some impurities in crude oil and so on. And from this I can calculate that the demand or the amount of hydrogen which is in these chemicals here is about 2.4 million tons. Yeah? So out of these 18 million tons here, there is about 2.4 million tons hydrogen. And this can be analyzed further. So if we want to produce then the cyclohexane here from hydrogen, then we can calculate, this is a chemical demand we have. We have 6 carbon dioxides plus 18 hydrogen molecules. The problem is that a significant share of the hydrogen from which we put into the process is not going to the synthetic fuel, but is going into the water. Yeah? So in fact, if we want to produce this from CO2 as a source, then we would need 3 times the amount of hydrogen, because 2/3 of the hydrogen are in the unvaluable water at the end of the day. Yeah? But nevertheless, the hydrogen needs to be produced. And this could be analyzed further with making some assumptions on efficiencies in the electrolysis, in the efficiency of producing hydrocarbons, and so on. And the demand now is, as I said, 3 times higher. So it's 7.2 million tons of hydrogen. And taking into account this efficiency, I know that I need about 55 kilowatt hours of energy per kilogram to produce the hydrogen. Yeah, so multiplying the 7.2 million tons of hydrogen with the amount of energy, electric energy I need, then I come up with an overall energy demand which is in the order of 400 terawatt hours. Yeah? This means about 3/4 of the current German electricity production would be necessary to reproduce the chemical energy or the hydrocarbons which are needed by the German, only by the German chemical industry when using electricity and carbon dioxide as raw products. And this is huge. Yeah? So this is why I say we should not put hydrogen everywhere where somebody would like to have it. But whatever you can produce, do it. Yeah? Because the demands are really endless. And the point is, Germany only has a relatively small share of the world crude oil demand, because this amounts to something more like 500 million tons. Because Germany as a country imports also lots of emissions, let me say, because many, especially cheap plastics and so on, are not even produced in Germany. We import them from the outside. So the emissions are somewhere else. Yeah. Maybe can we have a microphone? Can we have a microphone there? There it comes.
No.
Yeah.
How do you account for so the German electricity fuel source is natural gas to a certain percent? Are you taking into account so replacing crude and gas, and then the amount of electricity that you need? Are you talking about 100% renewable energy to give that? Or are you including also the natural gas, which is what you're wanting to replace?
First of all, I don't want to replace, I just want to compare. Yeah? So if I want to produce the hydrogen which is necessary here from electrolysis, I need about the 400 terawatt hours of electricity. So this is, first of all, the only thing I would like to say. What the source is doesn't matter. And I just want to say, to make clear what the orders of magnitude are we are talking about. That's just to make available a new CO2-free raw material to our organic chemical industry would require something like 3/4 of our current power production. And then it becomes very clear why we also say lots of these things need to be imported. We always should be aware that even not taking this into account, today the primary energy consumption in Germany is something like 3,200, 3,400 terawatt hours is a primary energy consumption. The electricity consumption is only 550. And the rest is all in these chemical materials, gas, oil, coal, and so on, and the losses. And yeah, a significant share is needed already for this.
And just aside, in the German politics, what is the sentiment for wanting to replace the crude and natural gas? Or from the petrochemical industry, right? Is there an equal interest for the population to want to replace the traditional oil and gas as an input for the petrochemical, or is it more balanced, or is it? I mean, because I imagine that the petrochemical industry, as you mentioned, for a long time had a very low cost for natural gas as an input, but that's probably been changed quite a bit recently.
And absolutely, this is why I say probably also the industry structure may change to a certain extent, not in all areas. Yeah? For example, in a car, the value of energy by producing a car is something like 0.6%. Yeah? So to be honest, if the energy would double in cost, you wouldn't have a major problem. But in basic chemical industry, it would be, but there's a lot of discussion about this, if this is really necessary. Yeah? Is it necessary to produce ammonia in Germany? Yeah? So if we can do this much cheaper in Saudi Arabia, because there is infinite sun, and we can import it, why not? And the number of workers working in this field is very low anyway, and as we have a shrinking population, we anyway have to look which of the industries we still can operate. But lots of discussion, no question.
One last, how do you see today the coal use will that be, and I don't know what the current, has it been limited in the past, but as you mentioned, your home is near coal. Will the coal use increase because of the issues in
it has increased last year, but this will not increase more than this in the last year, and I'm quite sure that we will have a fade out of coal toward the end of the decade. So there are political measures also to do so, but it will fade out due to the cost. Yeah, so this is really what the CO2 price does. So this is what we can see. In Great Britain, for example, they have reduced coal as a source for power production already years ago because they had a significant CO2 price already independent from the European Union for a long while. So this is faded out simply by economics.
Thank you.
Okay, so yeah, then we have the big problems I already have mentioned to a certain extent is that we have in some industries really very long-term investment cycles. For example, we are currently working with a company working in the glass production, and they have a melting pot where they melt the silicon as a raw material for the glass. And this melting pot is in operation 25 years continuously. And only every 25 years they stop this and let it cool down, and then you have to throw it completely away. So, and now the next cycle, or the current cycle ends 2025 or 2026. So the company now has to decide how to put the heating for this oven for the next cycle. And the next cycle then goes until 2050. And they looking for sure for using hydrogen as a heating source. But the big question is, where should they get the hydrogen from in 2025 or 26? And this is another reason why I say with the relatively rare hydrogen we have available, we first of all really have to support the industry with their very long-term investment cycles. Because they have to change over now. And I come at the end, I will also tell a little bit how the governments try to support these companies to stay competitive. This is that's another issue for sure as well. So the costs are high, no question, but the availability on its own is already significant. And what politics in Europe try to do for this is carbon contracts for difference and carbon border adjustment taxes. But the question is at the moment if these tools are sufficient, because at the moment we all look very scary. So how should I say? We look to the United States because in the United States this Inflation Reduction Act gives a lot of support to the companies there. And we see that for the companies it's very interesting to go to the United States rather than staying in Europe. So we will see what this all means. But nevertheless, these long-term investment cycles, same in the steel industry and so on, are the ones which are really difficult in chemical industries as well. Another field of where it becomes very obvious that different technologies are still also in a certain competition with each other, I would like to talk about trucks. So heavy trucks, I don't talk about the light-duty trucks. Light-duty trucks, I can say, for Europe, mainly the decision is made. They will go to full battery electric drivetrains. All the truck manufacturers more or less are 100% on this track. But the question is, what about the heavy trucks? Heavy truck in Europe means 40 tons. United States, we have even heavier trucks. I think here we discussed it's a little bit less. But when I talk about a heavy truck, that's the largest truck scale you can have. At the end, there are 4 different options to make them CO2 emission free. We could operate them further with the combustion engine, but using synthetic fuels. So if the synthetic fuel is made from green energy, then they would be emission free, is an option. Next option is to to drive them with fuel cell and hydrogen. Yeah, so this is an option. We have discussed already. The hydrogen probably needs to be stored liquid, in a liquid form. The reason simply is, if you put it just in pressure tanks, then the volumetric energy density is not much better than with a battery. And if you look to European trucks, heavy trucks, you can see that about 90% of the trucks are limited in their cargo not by weight, but by volume. Yeah, so 90% of the trucks do not really have a problem with some additional weight, but they would have problems if you would put more volume on it. And for the European legislation, we have a strict limit in the length of the trucks. Yeah, so this is also the reason why European trucks always have these flat fronts. In the United States, they have all these noses, which are much better with regard to air drag. The European trucks is the most terrible thing with air drag you can imagine. But the reason is simply because they are limited to 18.5 meters in length. And if you would put something in front, then you have to reduce your cargo area. So therefore, volume is a real challenge. So, and there are for sure companies developing in this direction, some startups going into this direction, but also cooperation of Daimler Truck and Volvo, for example, in Europe is developing in this direction, whereas Volvo, meanwhile, has announced that it will maybe take some time until they get to fuel cell trucks. As an intermediate solution, they will build battery trucks, battery-driven trucks. Filling stations, as we have seen, there are some filling stations available, so might be an option, but needs to be discussed. The third is using overhead catenaries. So putting overhead lines on the highways, as you can see here, and let the trucks drive as a tram, more or less, on overhead lines. In addition, these trucks would need a battery for maybe 80, 100 kilometers because these overhead lines could be installed only on highways. Otherwise, it would be much too expensive. Germany, for example, has about 13 to 15,000 kilometers of highways, but more than 300,000 kilometers of roads in general. So the idea is let them run the long distances on the highways. While they are driving on the highway, they can recharge the battery, and when they leave the highway, they can go the last mile on batteries. So this is an option, but not cheap. And you need a very high density of usage to become somehow economic. Maintenance demands are high, and so on. But there are in Europe, I think, 3 or 4 test lines for this technology, and I think 2 in Germany, 1 in Sweden, and maybe one else. And then finally, you can do it by battery. So many people think in the first instant, oh, much too heavy, and so on. But if you look to the operation, it can work, because at least for the European market, it is clear the truck must be able to drive up to 4.5 hours with one battery charge. Because after 4.5 hours, the driver must make a break by law of at least 45 minutes. And if we would make available chargers with the 1 megawatt power, then within 45 minutes, we can easily recharge the energy which is needed for another 4.5 hours. And this is technology which is available, and MAN or Traton, which is a Volkswagen truck company, but even others very clearly go into this direction. This is under discussion. The problem also is we need here, especially for Europe, we need a political decision, because we should have in the different European countries the same system. I don't want to have the trucks going on hydrogen in Poland, on battery in Germany, and on catenaries in France. The distances are not very high, and then we have to change the trucks or whatever. This makes no sense. So we need a general solution, but things are under discussion. But there are good reasons to go for batteries as well. For example, MAN did a very rough analysis already with McKinsey and others years ago, and they said from the life cycle cost of the truck operation, about 45% is fuel. The remaining 55% is purchasing the truck, maintenance, and cost for the driver. So 45% is fuel. And if the fuel is only a little bit more, if any fuel is a little bit more expensive than what the competitor can use, then you're out of the business. Because what you can earn is the margins are very small. And the hydrogen cannot be cheaper, at least not generally, because of the efficiencies. So this is not possible. And therefore, MAN decided already many years ago that their pathway won't be fuel cells. And they also think, when they look to the worldwide market, because truck is a worldwide business, this is not a simple German or European business, they think it's easier to roll out, for example, in Africa, charging infrastructure with PV and stationary battery than for fast charging of the trucks, rather than putting hydrogen infrastructure in place. I'm just citing what they have analyzed, but this is what they have looked at, and I have seen all the calculations they have done, as I said, with companies like McKinsey and so on. So this was very rough analysis. But we will see. But we need the decision, and this is so important. So this is just these four options once again. But we need infrastructure. And we need either fast charging infrastructure, which needs lots of investment, no doubt. We need, or we need the catenaries, or we need the hydrogen filling stations. But this is nothing which the market will decide. Because the market could decide only if you have all the three infrastructures in place already, and it must be more or less complete. So it doesn't make sense to have the one highway on hydrogen and the next one on electricity, because the trucks have to go the one day the one highway and the other one the other highway. So we need a political decision here, but the politicians say, oh, maybe we leave it open, technology open, and so on. And so it simply means we don't like to make a decision. But otherwise, we cannot build up infrastructure. So if we wouldn't have decided at a certain point of time that our grids should be AC, then we wouldn't have electricity until today. So, and this was a decision as well. No question. Or somebody decided on which side of the road you're going to drive. You cannot leave it open and say, oh, well, let us check. The one can drive left-hand side, the other one right-hand side. Let us see. So then some countries chose this way, the other this way, but nobody can change anymore. So this is, once you have decided for a certain path, you very much have to stick on this. So, and there are other applications for hydrogen-based products or not. So first of all, once again, there are lots of options or lots of technologies where you can use hydrogen. You can burn it, that's no question. The hydrogen turbines I talked about, this is from my point of view one of the most important technologies, because I haven't said this earlier, but if we build up wherever an energy system which is mainly based on renewables, you will have in parallel always a gas turbine infrastructure which is able to deliver almost the peak load, or at least the average load. Average load in Germany is 60 gigawatt, so we will need 60 gigawatt of gas turbines. This not sounds worse than it is, because gas turbines are relatively cheap. They are only expensive if they run, and they must not run many hours a year. But if there is no sun and no wind, we have to generate the power from the gas turbines. And therefore, we need a lot of this. So building gas turbines will be a key technology in the future. For sure, we can put it into fuel cells to produce electricity. We can put it into home heating systems. And hydrogen generally is a very flexible material. And as I said already, so hydrogen, or if I now say hydrogen, it could be also one of these derivatives like the synthetic fuels. The long-distance ships and airplanes, they will need something like biofuels, eFuels, hydrogen, and so on. They will not fly on batteries. This is different for short distances. So if you have ferries, for example, Norway, for example, is going very much into this now, the full electrified ferries. Also short distance aviation, so with maybe drones or whatever for cargo or for air taxis and so on. They will be on batteries most probably as well. But the long distance needs something else. And probably, for example, if we look to farming, this is also a big issue. Farm equipment very often operates far away from infrastructures. There won't be a fast charging station everywhere out on the rice field or on the wheat fields or wherever. No option. Or if we have harvesting period in the United States or in Europe, then the harvesters sometimes go 24 hours a day. This is not a business for batteries. And in addition, you also don't like to have these harvesting or these farming machines too heavy. Because otherwise they compress the soil, and this is not good for the farming in general. So they need something else. So we have to be flexible. Maybe they use biofuels. Could be a good idea. Maybe we can have on each of the farmhouses a small biofuel reactor or something like this. Or they use hydrogen or whatever. But what I just want to make clear is there is not the one-fits-all solution. So we really have to look carefully. And whereas on the road traffic, it will be relatively easy to do replacements also towards batteries. In off-road applications, farming, also construction machines for roads will be very difficult to electrify by batteries. Construction machines in city centers building skyscrapers, this is something different. And this is what I would like to make clear. Look carefully to each of these different things. And as I said, no one solution fits it all. For the aviation, so again, you can do some calculations about the demand in energy. So if you just want to replace the aviation fuel used by the German airlines tanked in Germany, this was about 11.4 billion liters of aviation fuel. We can do similar calculations as before. This would require something like 1.4 million tons of hydrogen, and is in total in energy, which equals about 14% of Germany's gross power demand at the moment. So again, you see, just for operating the airlines, this is a significant share of our energy consumption. Steel industry was mentioned already. At the end of the day, the first step is to reduce the iron oxide. What you get from the mines is iron oxide. And you have to get the oxygen out. Today we use carbon for this, so at the end the oxygen and the carbon go into a reaction at high temperatures, and what you get is pure iron on the one hand and carbon dioxide and carbon oxide on the other side. We can't use the carbon in the future anymore, so hydrogen is an alternative. This has been shown. The steel manufacturers have developed these processes in the last years. Generally, they are ready to build steel manufacturing sites based on hydrogen. But again, they need the hydrogen. So I showed the problems in supplying the hydrogen. And again, if somebody builds a new steel factory now, it should be ready for the use for 40 years roughly. So we have to supply them with hydrogen with the small amounts we really have. In stationary applications, I have mentioned several times, we needed to stabilize the grid directly, whereas on the other hand, for the house heating systems, here we have alternatives. This is about the discussions we have in Germany. As I said, there are very strong forces from the operators of the gas distribution systems that the replacement for the house heating should be hydrogen instead of the natural gas. But this is really inefficient, and we simply don't have it. We better should invest into enhancing the electrical distribution grids, And then in the future, we will have only one distribution grid anymore, and this is electricity to the houses. Today, we have two, gas, or three, better to say. We have water, we have gas, and we have electricity. In the future, we need two of them, water and electricity. This might be different if we talk about huge skyscrapers in city centers and so on. Maybe there it is better to still serve gas and then having maybe cogeneration units in the houses and so on. Again, this needs to be looked at very separately. Same discussions with trains. So local trains, short distance trains, 50 to 150 kilometers of range. In a country, or in Germany, for example, we have roughly, I think, 50% of our rail tracks are not electrified. They only have maybe 15% of the overall traffic. So the main traffic runs on the full electrified lines, all the long-distance trains and so on. But nevertheless, there are quite a sufficient number of trains running with diesel engines still, and this needs to be replaced as well. And again, the question is this an example for using hydrogen in the future, or is it a battery? This is really like a fight between different groups. And there are lots of calculations. The business-based calculations typically end up with a battery-driven system. And if it's political driven, it's getting hydrogen. The local mayors and so on, they all love hydrogen. This is also the reason why we have so many hydrogen filling stations in Germany, because the local mayors always say, okay, I would like to have one more. But if it comes really to full economic calculations, typically it does not end up with hydrogen. Because the problem is, in what I haven't mentioned yet, I just talked about cost for hydrogen production from renewables and transport, but this is not price. So if you look to oil, for example, I think digging oil, you know it probably better. In Saudi Arabia, the cost is in the range of $10 per barrel. If Saudi Arabia produces oil, and the price on the world market depends, $50 to $80 per barrel. So there is a certain range between cost and price. And at least for quite a while, as long as hydrogen will be really a rare material, the price will be significantly above the cost. And nobody really knows where it will be. What we can do is cost calculations. So this is a baseline. But what the prices will be is much more difficult. Yes, please.
I have a question regarding the future of the train as well. As there are going to be more renewable energy production all over the countries, will there be a chance that you actually have like electrical line more for the train that is not already electrified at the moment? Or do you think it's not going to be cost effective still? Or is it going to be a possibility of a hybrid, a battery with some of the part that is going to be electrified and charged along the way?
The reason that probably everywhere, the reason is if the train tracks are not electrified is cost. Overhead lines is something some infrastructure which is really expensive, not only in the investment but also in the maintenance. So this is typically quite clear, and this is not changing due to additional power generation. The amount of electrical power which is used by German trains is in the order of maybe 2% or something like this from the overall power generation. So we are not limited by electrical power. We are limited by the cost. And indeed, the question is how to electrify then. And if we would do it with batteries, then you have more or less three options. The first option is you just recharge the battery at the beginning and the end of a line. The second is you recharge for the 2 minutes, maybe a train stops at the different intermediate stops. Then you will have a catenary which goes upwards, and then for 2 minutes you push quite a high power in the battery, and then together with charging at the beginning, at the end, you can go the distance. Or the other one is, you may call it a hybrid, but we call it in motion charging. Yeah? So this means maybe you have 10% of the whole line electrified, and during these 10% of time, you take relatively high power to recharge the batteries. So even for trucks, yeah, Siemens 2-3 years ago proposed a system even for the catenaries for trucks to have maybe 1 kilometer overhead line, and then the next 3 kilometers don't have overhead lines. Yeah? So you always 1 kilometer, you take electricity directly and charge the battery, and the next 3 kilometers you drive on the battery, and so on and so on, to reduce the overall length of these overhead lines. And something like this, maybe not with 1 kilometer, 3 kilometers, and so on, but maybe 10 kilometers overhead line, next 30 kilometers no, or something like this. These are all options, and at the end of the day, you have to calculate it. Again, it has to do a lot with infrastructure. Sometimes if you really drive into the countryside, maybe at the end of the line, you don't have a powerful electricity system. Yeah? And then either you have to install one there. This is an option, yeah, to put an independent PV systems, for example, on site with a stationary battery. And with a PV system, you charge continuously the stationary battery. And if the train comes, you transfer the energy at high rate from the stationary battery into the train. This is an alternative. And in many cases, it will be cheaper than building maybe a new medium voltage line over tens of kilometers to the point. Or maybe the solution is hydrogen. So you have to check. So, and as I said, just showing here examples from the German debate. So there's a battery train rolling and driving in Schleswig-Holstein. This is of a northern local state. And another place in Hessen, we have hydrogen trains. And in Niederrhein, this is close to Aachen, it is a battery train. And in Baden-Württemberg, it's again a hydrogen train. So, but these things are not yet, these decisions are not yet really based on economic calculations. These are all political decisions. The politicians beforehand say, I would like to have a fuel cell train. And then they get a fuel cell train, obviously, because the train manufacturers build them, so they are generally available. So, and I think most of these things I have mentioned, there are several fields where hydrogen really is without alternative. Others, there are alternatives, and others, there it is clear what technology should be chosen. This is where we're really looking at. So, and at the very end, just in short, a few political implications. Because first of all, I already have mentioned, it become really difficult to be something like a first mover. First of all, from a technical point of view, there was people from economics. From a business school, he said, in these days, there's almost no benefit anymore from being something like a first mover. Because at the end of the day, all technologies can be copied. So as a first mover, you have a lot of additional cost, and you don't know how far you get, and the standards are not defined well, and so on. But the benefits you have in the market compared with competitors is very limited. And I mentioned somewhat earlier, for example, in the field of electromobility, there are companies like Tesla working since 15 years on electric vehicles, conventional car manufacturers maybe since 10 years, but now there are coming new competitors from China, for example, just startups 2 or 3 years old. And within very short time, then they can catch up the technology, and they are full competitors. So the first movers have very little advantages. But at the same point of time, especially when we talk about such a worldwide good in trading, yeah, so, or a good which you can trade worldwide, yeah, you have full competition. The ones who invest now have significantly higher cost for all the installations. The electrolyzers are more expensive than in the future. The Fischer-Tropsch or Sabatier elements are more expensive. Even the renewable power generators still will see a decrease in cost. So who is going to invest now has very high investment cost. And the question is, will they be beaten on the markets with a hydrogen price by those who invest in 5 years from now, maybe? Some people say, no, this won't be a big problem. Taking again the example of oil. So digging for the oil is significantly cheaper than the market price. So there's a large gap. So even if you have maybe double production costs, you still can earn money on the markets. The question is if this will be the case with hydrogen. In the medium to long-term run, I expect that the difference between cost of hydrogen and price of hydrogen will be significantly smaller than for oil or gas these days. Because the number of countries and sites and the potential to produce hydrogen are more or less unlimited. Whereas oil and gas is very limited to a few countries and few sites and so on. So this can be very well controlled. The hydrogen generally is very flexible technology, can be produced more or less everywhere in the world. But this will take time until really the demands are more or less covered. But getting into this is extremely difficult. The question is who is going to be the first movers, and the question on the other hand is what does it mean for the politics? How can they support their countries, or how can they push the companies in this field? And for this this problem with the price decrease, I would like to show you an example which not comes from hydrogen but from batteries. It's about batteries in the field of frequency control. So this is a service to the grid. And here you can see battery systems which have been built in different years, starting in 2013 here, the first megawatt storage system, and going further. And if we look now to the market first of all, so this is what you can earn here per week on the European frequency control market. This is the European market, and this was somewhat changing over the years. And when the first battery system in 2013 was built, the cost of the system were about at 1.2 million euros per megawatt. And you can see, or the orange line shows what the market price have to be for at least 10 years to refinance this investment. And you can see when the system was installed, it was okay, then it was somewhat higher, but meanwhile we have a clear trend of the price to lower values, and so this battery system is not earning enough money anymore because the market price is lower than what is necessary to do the refinancing. Why is this the case? Most important case is there came other battery systems. There were systems installed in 2016, for example. They were a little bit cheaper, 10% cheaper more or less. There were systems in 2018. They were almost already at half of the price here. And today we are probably even lower in the price. So the new build systems all are built at lower cost. So as all of these companies give a bidding to the power exchange, and they do this bidding every 4 hours. So if you win a bidding, you have a contract for 4 hours, not more than this. And this simply means those who have the lower investment costs can do for sure lower biddings because they still earn money. And this means those who have invested first are out of money. Stranded investment. That's a real problem if you go into this. The way how this was overcome in the field of renewables in Germany and many other countries was by installing what we call the renewable feeding law. Yeah? Simply speaking, this means the companies got a fixed price for 20 years of operation according to the average technology cost in the year of installation. So they did not make huge wins from this, but based on the cost, they got what is necessary, and those who invested the years later got a lower price for the electricity, still enough to refinance the system over 20 years, and by this the price dropped and dropped and dropped very well. This worked very well, but the companies who did the investment had a 20 years guaranteed price, which resulted, generally as a side remark, also in generally quite lower cost, because the banks were willing to give the bank loans at a relatively low interest rate because there was a governmental guarantee for 20 years of repayments. If you go to a full competitive market, then there's a high risk that you may not refinance your investment, and then you have to pay from the very beginning higher interest rates, means more expensive power generation, and so on. And these problems generally occur in the same way with the international hydrogen economy, and therefore Europe, Germany, others try to put some things in place where they as well guarantee somehow those who are the first movers fixed prices for a relatively long while to give them the chance to get refinanced. And two other tools to protect the industry or to support the industry are the so-called carbon contracts for difference. This is something which is attributed directly to the companies. I come back to the example of the glass manufacturer. If this glass manufacturer now in 2025, 2026 switches over to hydrogen, this will be most probably more expensive in operation than if they would have continued in 2026, first of all with fossil fuels. Because the technology is new, the question is where to get the hydrogen from, and so on. But these carbon contracts for difference will compensate for the company the difference in the cost between the conventional operation and their operational cost for a certain number of years. And probably from year to year, this difference will get smaller and smaller anyway. Because we still expect that the price for CO2 certificates will still rise. This means the fossil-operated sites getting more expensive in operation step by step, whereas the renewables more or less stay at constant cost. So at a certain point of time, you will have a crossing point, and from this point onwards, the company who have switched over to the CO2-free production relatively early will be has an advantage compared with those who still work with the fossil fuels. But as long as this crossing point is achieved, the government will compensate for the difference between these fossil fuel operation compared with the renewable operation with the renewable hydrogen or renewable electricity. This means more or less carbon contract for difference. So this is one tool which can help companies to make a decision to switch over, even though technology might be still expensive at this point in time, and to still keep them competitive with the world markets and with their direct competitors. And the other thing which is discussed is carbon border adjustment tax. At the moment, this is discussed only for 4 or 5 different segments: steel, cement, aluminium, fertilizers, and energy. And this simply means that companies who would like to import, for example, steel to Europe, there it will be analyzed what is the specific CO2 emission in the country of origin or in the factory of origin compared with the average CO2 emissions or greenhouse gas emissions in Europe, and the difference will be taxed maybe with the fee for the CO2 trading, CO2 trading price. This should assure On the one hand, again, that there is not coming cheap material into Europe, which was produced with a lot of CO2 emissions, which on the one hand would be a real problem for the European industry on the one hand, but which also would result in a shift of the energy-intensive and CO2 emission-intensive industry to somewhere else, which doesn't help the climate at all. Yeah? As tons of CO2 has the same impact on the climate if it has been emitted in Germany or somewhere else in the world. Yeah? So this should be avoided, and therefore these carbon border adjustment taxes are under discussion. Very difficult, yeah, because this is very difficult to bring in line with United Nations trading treaties and so on. But nevertheless, we see more and more of these things. United States, just mentioned, have put these Inflation Reduction Act into power, which goes another way. It defines, on the one hand, it gives high tax reductions for investments, but on the other hand, it defines very high local content rates. Yeah? So if you want to build an electric vehicle in the United States, you have to produce a battery in the United States, full stop. Yeah? You cannot import it anymore. Yeah? And this is another way of enhancing or protecting the national industry. And what we really see is somehow a flip back. Yeah? So where in the last 20, 30 years, free world trading was the highest target and goal of international politics. Now it returns pretty much in many different fields to a much more localized industry where governments protecting their industries individually. This will not be good in total for the overall world economics, but if one starts with this, it's very difficult for the others not to do similar measures. As I said, we wouldn't need, for example, these carbon border adjustment taxes. It would be possible to convince all other countries in the world to take part in the same CO2 trading mechanism. Yeah? Because then we would have a world market in CO2. Everybody pays the same. All the emissions would be included, but this is not more than a dream, and a dream very, very far away. Yeah? So some politicians in Europe hope that there might be a coalition of the willing, maybe with 6, 7 major industrial areas in the world, but especially under the conditions we have today, this is all not very likely, I have to say. All right, so summing up the long day seminar. The energy system will become much more electric. Very clear, because the input of energy is electric. Yeah? Once again, renewables, some would add nuclear technologies, but they also produce electricity. Material-based energy carriers will be necessary, no doubt, and in various applications, but hydrogen will remain for a long while a very rare good, and it won't be cheap. Yeah? So somebody in Germany called it the champagne of the energy transition. Yeah? On the one hand, champagne is something very nice, but also champagne is a synonym for expensive. Yeah? So it's both. Yeah? It's very nice to have it, absolutely necessary, but not cheap in the near future. Therefore, applications must be carefully evaluated. Are hydrogen or e-fuels necessary? Are there alternatives with direct use, cable, or indirect use by battery of electrical power? And then decisions have to be made. A world hydrogen economy just starts to establish. It's a very early stage, and it starts from a very low level, as you have seen, with regard to electrolyzer capacity, shipping capacities, and so on and so on. And in any case, first of all, renewable power generation capacities in huge quantities are necessary, because otherwise we won't have the electrical power for the power system on the one hand, but also for producing hydrogen and the fuels. So we must not talk about a hydrogen economy without really dramatically increasing the installation of renewable power generation. So this is key. And the other thing comes one step later, more or less. Nevertheless, it needs to be developed at the time because we have seen time constants. For example, once again, in the automotive sector, the real thinking about lithium-ion-based full electric vehicles started maybe around 2008, so something like this. So now in 2023, we may have achieved a world market share of 10%, so 25 years later. So this is very typical. 10% is already very good, because if it now grows by 30% per year, then it's 100% very soon. But try to get in a new market to 10%. This is really the challenge, and this is very normal. And this is the same, we will see this in other sectors as well. We cannot grow with infinite gradients. This is not possible. So by this, I would like to stop here, and now again, time